Section 8.4, part 2, let's pick it up with example 3, which adds a few more words. Now remember our formula. Our formula says the combination of n trials taken x at a time times p raised to the x power, where p is the probability of success, times q raised to the n minus x power, where q is the probability of not success. So in example 3a, we're going to use the formula to determine the probability of exactly 4 successes in 7 trials of a binomial experiment in which p is equal to 2/3. So we now need to come in and figure out what n and x are. Well, they tell me that p is 2/3. So at least I've got that much going for us. We know that we have a total of 4 successes in 7 trials. So n is always the larger number. So n is going to be the 7, and we're looking for specifically 4 successes. And then we can plug it into our formula. So the probability then, and if you want to label it further, you could call it just probability of 4, because that's what we're looking for. So it would be the combination of 7 choose 4 times the 2/3 raised to the 4th power. Q again is going to be the complement, which would be 1/3, raised to the 7 minus 4, which is the 3rd power. Then you head to your calculator, number crunch that through, and you should end up with 0.256. And hopefully you are number crunching to make sure you get my answer. Part B on that example says, let's find the probability of no successful outcomes in 6 trials of a binomial experiment in which p is equal to 0.4. So p is 0.4. We want no successes this time in 6 trials. So n is going to be 6 and x is going to be 0. So we don't want any successes. Using our formula, we'll get the combination of 6 choose 0 times 0.4 to the 0 power times the complement to 0.4 would be 0.6, because again, they have to add to 1. And that'll be to the 6 minus 0, which is 6. So this is pretty easy. The combination of 6 choose 1 is 1. I'm sorry, 6 choose 0 is just 1. 0.4 raised to 0 power is 1. So really the only thing that influences the answer is this 0.6 raised to the 6th power. And 0.6 raised to the 6th power is 0.0467. Okay, let's actually try and do one where they're not hand feeding us everything. So we're going to go take a look at a 4-child family. So our next example reads, let the random variable x denote the number of girls in a 4-child family. So n is going to be the 4 kids that are in the family. If the probability of a female birth is 0.5, we want to find each of the following. So part A says, let's find the probabilities for 0, 1, 2, 3, and 4 girls in a 4-child family using the binomial probability. So we've done this kind of problem before using our counting techniques way back in chapter 7. This time we're going to use the binomial experiment to show you how much quicker it is. So let's come in and do each of those. So first we're going to do no girls. So that would be 0.5 to the 0 power. His complement is also 0.5 to the 4 minus 0, which is the 4th power. So this is the probability of having no girls, and that comes out to be 0.0625. Now, we did this before, and when we did it before, we did it this way. So just note to self that on a 4-child family, that would be 2 to the 4th outcomes, which is 16. And to have no girls, you only have 1 boy. There's only one way to have no girls. That's if you have all boys. So the probability of no girls, when we did it in chapter 7, was 1 out of 16. If you take 1 divided by 16, you're going to end up with that. So, okay, now let's come in and figure out the number of ways to have 1 girl. So that would be 1 girl amongst the 4 children. We're going to do 0.5 to the 0 power. Sorry, that's 0.5 to the 1st power. And then we're going to have 0.5 to the 1 from 4 is 3. And heading to the calculator, that one comes out to be 0.25. If you want to have 2 girls, so 2 girls, 0.5 to the 2nd power times 0.5 to the 2nd power. That one comes out to be 0.375. And if we want to have 3 girls in our family, the probability of having 3 girls in that 4-child family, it's a combination of 4 choose 3 times 0.5 to the 3rd power times 0.5 to the first power. And that comes out to be 0.25 also. And then finally, the combination of having 4 girls in that 4-child family. That's it. We're going to multiply that by the 0.5 to the 4th power times 0.5 to the 0 power. And we're going to come and do this. And when you do this, the combination of 4 choose 4 is 1. 0.5 to the 0 power is 1. So it really comes down to this 0.5 to the 4th power, which is 0.0625. So again, no girls, 1 girl, 2 girls, 3 girls, all 4 girls. And if you sum this up, you should get your 1. So, because those are the only possibilities when you have a 4-child family. Part B says to construct the binomial distribution and draw the histogram associated with the experiment. So the distribution, and I'll definitely run out of room, would be this. So we would have no girls, 1 girl, 2 girls, 3 girls, or all 4 girls. And we said that this was 0.0625. This was 0.25, 0.375, 0.25, and then the 0.0625. So the histogram, we're going to see. So number of girls, so 0, 1, 2, 3, 4. And over here, I'm just going to count by 0.2. So 0.2, 0.4, 0.6, 8, and 1.0. So our first one at 0.0625 is pretty tiny down here. The 1 girl is 0.25, a little bit taller. 0.375 for the 2 girls, and then it comes back down. And we're going to see that it's a very symmetric distribution, and you can see that from the numbers themselves, right? So we can see the symmetry with that. Okay, and there's the histogram associated with this experiment. Okay, let's take it outside of the child, the families. Do another example. So example 5. If the probability that a certain tennis player will serve an ace is 1/4. So we consider the serving an ace to be our success. We know P is equal to 1/4. What's the probability that he will serve exactly 2 aces out of the 5 serves? So exactly 2 aces out of the 5 serves. So N is 5, X is going to be 2. So the probability would be the 5, choose 2, the combination of 5, choose 2, times that 1/4 raised to the 2nd power, times 3/4, and again, 5 minus 2 would give me 3. So, that is it. And again, you head to your calculator. When you're doing these in the calculator, make sure you put parentheses around those fractions, otherwise you'll get some really bizarre answers. It can't possibly be correct. And we have a 0.264. So the probability that that tennis player will serve exactly 2 out of the 5 comes out to be 0.264.